We're going to look at a new method for finding the volume of solids that are generated by revolving regions about axes. So here we're going to take the region bounded by this curve, which is 4x minus x cubed, the end of the x-axis, so the inside region here, and we're going to revolve it about the y-axis. Okay? The method that we're going to use is what's known as the volume, or the method of cylindrical shells. And it's a little bit different than the disc and washer method. Okay. Now, if I really wanted to do this by the disc and washer method, since I'm revolving about the y-axis, I would have to find an equation for this part of the curve and find the volume generated by revolving just that portion. Now that would also require we figure out what the maximum value is. Don't know if I'd be able to do that. I probably could use a little calculus. But revolve it about the y-axis and then take this portion and find the volume that would be generated by revolving the region over here about the y-axis and subtracting the two. Okay, it's a little bit messy, and the real problem is that there's no really nice way to solve this for x, because that would be required. We'd have to find an equation x equals something here, and then an equation for this portion as well. So the volume by cylindrical shells will save us from this. So what we'll do is we'll start off by looking at a typical rectangle. Now in the disc method, we took this rectangle and revolved it about the x-axis on certain circumstances, and that would produce a long, thin disc here. But this time what we're going to do is we're going to take the same type of rectangle. Since we're revolving about the y-axis, we're going to revolve it around this way, and it generates a different type of creature. It generates what we call a shell. Okay, and so what we'll do is we'll take rectangles all the way across and add up the volumes of these shells. It's a little bit more complex than the disc method, but if you really think it through, you can do these problems without too much trouble. Okay, so what we're going to do is we need to figure out a formula for the volume of this shell. Well, the best thing to do is to imagine slicing the shell open. Okay, so maybe we slice it along here, and then we roll it out. Okay, well, it's not quite, but it's basically like a little box when we do that. And the area of a box is length times width times height. Well, the height of the box is just a very thin distance here, okay? And the width or length, whichever you want to call it, one of the dimensions would be this way, and the other dimension, either the length or the width, will be the distance around this shell, which is the circumference. So really what we need here, the volume of the shell is the circumference of the shell. That's one dimension of the box that I would get when I slice it open and lay it out. Multiplied by the height of the shell, that's another one of the three dimensions, and then multiply by the thickness. Well, the thickness is pretty easy. The thickness is just dx. Okay. How do we get, well, let's work backwards. How do we get the height? Well, the height is going to be this distance here. And if we just take an x and y value, this is going to be the function value that we have here. Now, we might be able to take regions between curves and revolve them, so you might have to do something a little bit different than just lay out the function value. But you need to figure out what the height of the shell is, and often it's written in terms of the function values. The last thing we need to do is figure out the circumference, and either the formula for circumference is 2 pi times the radius, so I need to figure out what the radius is here. Well, the radius, I'm going to show it down here. There's my height. The radius is the distance from the axis to where we intersect the curve, which is just the x value. So the height, or the radius in this case, is x, and the circumference will be 2 pi times x. So we put all these pieces together. The circumference is 2 pi times x, the height is our function multiplied by dx, the volume of our shell will be this. Now in general, we can make general statements about this. The only thing we'll really change is what's inside here. That's our function value. The 2 pi times x will stay the same, the dx will stay the same as the thickness. It's this function inside that will change. And again, we have to be careful about whether or not we need to trap the region between two curves or something like that. So I may have an initial difference here. And depending on whether or not we revolve it about the y-axis, maybe I revolve it about some other line x equals -1, well, the radius would change just a little bit then. Okay, but to find this volume, we'll just add up all those shells. Again, well, that's taking an integral. And we're going to integrate from 0 to 2 because our upper limit is 2. That's where we intersect down here. We expand the x, or distribute the x through to get 4x squared minus x to the fourth, and use our formulas for finding antiderivatives, and find out that our volume of this creature is going to be 128 pi over 15.